Hyunseung Kang with us. And Hyunseung is going to teach us on the blackboard the foundations of instrumental variables. And this is a big literature. Tingwan often, I don't know, he's not here now, but when he teaches, he usually says, if you start with the Ivy model, you can teach pretty much everything about Causal Inference. There's so many, with that simple model or that simple structure, you can teach so many of the subtleties of Causal Inference. Hyunseung, he has made several clever and important contributions to the methodological literature and theoretical literature on instrumental variables. And he also touched on many different applications, from biomedicine to the social science. Welcome.
Well, thank you for the organize. Oh, I guess I'm one of the organizers. Thank you for letting me take the opportunity to give you about a 2-hour lecture on IVs. I was debating last week on whether to put it on slides or not, but actually I have done a version of this, an hour 45 minute on IVs on a chalkboard before last semester during my sabbatical at Rutgers with both the semi-parametric folks as well as the design-based folks, and I thought they really liked the chalkboard style where I can kind of slow down a lot and then really answer questions and add commentary along the way as well. So I hope this is very useful. I've already posted on the Slack channel the entire notes that I used to go through this material. Feel free to look through it. It also gives you my link to my teaching website where it goes through all of how I interpret causal inference and how I teach it, usually to undergraduates, advanced undergraduates at the end of the day. And at any time, feel free to stop me if you have any questions. Okay, so with that, the first part of the talk, we'll try to get to a point where we go up to monotonicity, which is one of the assumptions that defines an instrument. And then the second part of the talk, we'll talk about the more additive interaction approach, which is, I would say, a structural approach. You kind of have to believe that the structural model exists and then that there's certain no interactions in that structural model to do so. Okay. Any questions before I begin? And again, for the people in the back, if you can't see, either refer to my lecture notes on Slack or please raise your hand and I'm happy to clarify. All right, so we begin. We begin with a very brief review of strong ignorability. This was briefly touched on yesterday on how do you identify causal effects from data, observed data at the end of the day. And one of the most popular assumptions to do so, there are various names for it, is strong ignorability, and it can be roughly summarized into these 3 assumptions. Again, here just to denote, Y is the outcome. A is the binary treatment, and this is the counterfactual outcome under treatment, and this is the counterfactual outcome under control. And then strong ignorability roughly asserts, so this is strong ignorability A2 and A3, but roughly these 3 assumptions are typical to identify a causal effect. The first assumption is that the observed outcome is one instance of the 2 counterfactual outcomes, either the counterfactual under treatment, which is denoted by A here, or the counterfactual outcome under control, which is denoted by 1 minus A here. The second 2, the last 2 are really known as strong ignorability by Rosenbaum and Rubin, 1983, and it's a combination of 2 assumptions. The first assumption says that the treatment is independent of these counterfactual outcomes given X, so conditional on some X variables, measure covariates. Your treatment is as if randomized in the experiment or in the design that you're studying. The third assumption, called positivity, or in the original paper called it overlap, says that essentially the probability of receiving treatment for every possible X is in between 0 and 1. In other words, for every strata of the person defined by X, you have a non-zero probability of receiving treatment or control. Yes?
In your notes, I'm just pulling up your notes. I mean, you're not using the joint independence, right, anywhere. You're just using marginal independence.
Joint independence of this guy here?
Yeah.
Yes, I think you can definitely use, there are many variations of this. You can use based on mean independence, joint independence, so you can take this one out, and you can also not do it based on joint independence. We're just going to assume the simplest possible just to make the presentation.
Why is it the simplest?
Because I don't then have to deal with writing this 2 more lines of the 1 and 0 at the end of the day.
It's syntactically simple.
Syntactically simplest, yes. It's not mathematically simple, but syntactically simplest. But thanks, Ilya, for the compliment. So these are roughly the 3 assumptions that are typical to identify, let's say, the average treatment effect. So under 1 through 3, you can identify this parameter, which is, you can think of it as a low-dimensional functional of the counterfactual distribution of y1 and y0. As just essentially an averaging of regression functions. You take you compute the expected outcome of y given under the treatment assignment, undertreated for some x, and then you do the same for the control. You take the difference of them, you average that difference, and that will give you identify the average treatment effect. Now you can also use all these assumptions to identify other parameters. This is a little bit stronger to identify the average treatment effect undertreated. You can also identify policies, optimal policies, and if you're interested in that, my lecture notes that precedes this one talks about identifying optimal policies, value functions, static regimes, just using those 3 assumptions. Again, these are a little bit more stronger than necessary, but kind of gets to the point of how the identification. Now, the key problem, or at least one of the key problems in using these assumptions is that A2, this assumption on ignorability or conditional exchangeability, can be violated. And I'll go through 2 reasons why it can be violated. So the first reason is essentially a non-compliance in a randomized control experiment, or sometimes it's known as a broken RCT, or sometimes it's known as a quasi-experiment at the end of the day. And how this works is as follows. So suppose you're an investigator and you want to run an RCT to evaluate like a new program versus a standard program. So the new program will be denoted as A equals to 1, and then the standard program will be denoted as A equals to 0 here at the end of the day. So the investigator randomizes some participants into the new program, and the other participants in the standard program. But after randomization, participants may deviate from that random assignment. They may do 1 or 2 following things here. So if you define this variable d, which denoted as, I'm going to call it treatment receipt, where d equals to 1 represents, is denoting a participant that uses the new program. D equals to 0 represents a participant that uses the standard program. And we're going to just kind of ignore the notation a little bit here. YD is going to also denote a counterfactual outcome of actually using the program D here. Under this case, the usage of the program is not randomized at the end. The initial randomization was done on whether you actually intend to assign the treatment, what's called in the literature. But maybe the participant may actually not actually use the program that's randomized at the end of the day. For example, the participant may be randomized to the new program A equals to 1, but maybe they decide, I don't like the new program, and then they decide to not use the program. So that will be a participant that is A equals to 1, but D equals to 0. Or maybe the participant that was randomized to standard program, so A equals to 0, may actually decide later down the road they want to actually use the new program. So this will be a participant who goes from A equals to 0 to D equals to 1 at the end of the day. Okay. Because of this, you no longer have the fact that the D is independent of the counterfactual outcomes of y1, y0, and x at the end of the day. Okay? And this also means that you can no longer use that particular identifying equation to directly identify the effect of using the program on the outcome of interest. Okay. Now, one way to proceed if you feel like this is a violation is to simply, well, one literature would like to proceed is to simply collect as many covariates as possible to pretend that the usage of the program is randomized, as if random, conditional on sufficient number of x's that you collect at the end of the day. And if that's the case, then we go back to the original case of strong ignorability, except instead of A, we now have D at the end of the day. And the counterfactual outcomes are defined differently. Any questions on the reason for why A2 might be violated here in some sense? And that if you want to estimate the usage of the program, you would not be able to use this kind of strategy to estimate the counterfactual effect of using the program. Now the second thing that's probably the most popular reason is essentially there's an unmeasured confounder U that dictates whether you're going to take the treatment or not at the end of the day. So suppose you believe that the treatment assignment, somebody's propensity to actually take the treatment depends on both. So someone's depends on both x and what I'll denote as u and U here denotes some unmeasured variables at the end of the day. So maybe somebody's propensity to use the program depends maybe not only on their age, but also some characteristics, some underlying characteristics about health that we're not able to measure at the end of the day. And in this case, we can kind of go play this game a little bit by saying maybe after you observe both X and these unmeasured variables U, the treatment itself is as if random. So maybe after observing U, you believe that this is true, and then this is true for all X and U. Okay. If you believe so, you can immediately see that those two assumptions do not necessarily correspond to that assumption here, right? This assumption, A is only random conditional on X here, but if you believe that there's an unmeasured confounder, unmeasured variables, and these things are known as unmeasured confounders if you define this way, treatment is randomly assigned after conditioning on X and U, then you can kind of, you can use this equation here, but then you would have to condition on U, which is not observed. Okay. Another way to say this is that you could go through this way, but if you do so, using this approach, you would have to essentially run a regression function, estimate a regression that depends on both the measured variables X as well as the unmeasured variables U. Okay. And that's not possible at the end of the day. Okay, so these are the two main reasons that you can entertain to assess violations of A2. So the entirety of, oh yes, please.
This is a bit theoretical to me.
Okay.
So, could you model the reason 1 as a time varying treatment?
You could definitely, so I'm talking here about static, single time point treatment, but you could also extend this framework to time varying treatment where you, let's say, have a sequential treatment assignment as you go along the time, and you may have unmeasured variables that dictate, let's say, your treatment assignment time point 2 based on not only measured variables at time point 1, but also unmeasured things that happen at time point 1. In this lecture here, we're only focusing on just you assign treatment at one single time point, and everyone's assigned treatment at that time point. Yeah, does that answer your question? Yes?
Big question. So in number 4, is the fine still on in terms of intervention on A, or is that on intervention on D? Just independence state, or actually no independence state.
Yes. So I'm kind of using notation a little bit here, but I just for this little 5 minutes, I redefined the potentiality in terms of ID. This will go away literally after 5 minutes, literally after this. Any other questions? I also realized from lunch yesterday there's a lot of diverse audience here, so some are more theoretical and some are very applied, and so feel free to stop me if you have any questions along the way. Okay, so given a potential violation of A2, an instrument tries to solve this problem by allowing for situations like this on the left-hand side, on your right-hand side, by constructing or finding a variable Z instrument that satisfies 3 assumptions. So let me go through roughly what those 3 assumptions look like in the literature. So let me take a moment to erase this guy. So roughly speaking, the IV variable Z instrument if, and this is just a rough version, we'll make this precise, these 3 things hold, Z is related to the treatment. Z is independent. Of all confounders. That affect Y and A. And then finally, Z only affects the outcome Y through A. Okay. Now, there's a lot of air quotes here because these are not precise yet, but roughly speaking, an instrument is a variable that satisfies these three what are known as core conditions. This instrument has to be related to the treatment, and we'll make this very precise in the next 35 minutes. The instrument has to be independent of all confounders that affect Y and A. This should be quite obvious. Essentially, the Z has to be independent of the X and U variable there. And then Z only affects, and FX is in quotes because this can be defined various ways, the outcome of Y through the treatment variable A. Okay. Now, depending on how you make these three statements precise, defines the two separate literatures in IV, the monotonicity-based literature or the no additive interaction effect literature. The no additive interaction effect literature makes slightly different assumptions about what this looks like, as well as further assumptions that I'll talk about on how this looks like. The monotonicity literature also slightly defines these things a little slightly differently, and so we're going to go through in the first part of the talk on the monotonicity-based approach. Yes?
Into, you mean unmeasured confounders? Right?
Yes, actually, yeah, all confounders including measured and unmeasured, but you're right. Actually, yeah, sorry, unmeasured, you're right. Yep. Thank you.
So not measured?
Yes, so not measured. So things like U over there. In this last slide here, this Z has to be essentially independent of unmeasured confounders of X and U. I'll explain what this Z looks like. In fact, there's a nice way to construct this Z through design, and the most classic design is the randomized encouragement design, where you can actually construct an instrument based on the design. So, let's talk about formalizing these three assumptions using the monotonicity-based approach. And this is the one that won the Nobel Prize about 3 or 4 years ago now. And Ito doesn't think it is the most significant achievement of his lifetime, but it is what really drove this field in the 1990s and onward at the end. So to do this, it's best actually to kind of think of a design. So the design that actually motivates all these assumptions, and the most common, the most prototypical one is known as the randomized encouragement design. And to the best of my knowledge, I think the first instance of this was by Sexton and Hebel, sorry. In 1984. Again, all the references are in the lecture notes if you're curious about following, tracking these down as well. Okay. So, they had an interesting conundrum. They wanted to study the causal effect of smoking during pregnancy, of maternal smoking, pregnant, on the birth weight of the child. Okay. 1984, smoking was still considered to be a causal agent of various things, but this was an interesting question that they proposed. What is the causal effect of smoking during pregnancy on the birth weight of the child? Okay. Now, by the way, it's bad. You shouldn't smoke. Okay. This is no longer a question anymore. But back then, they wanted to answer this question. Okay. Now, one way to do this without knowing an instrument is to randomize mothers to smoke or not smoke. Okay. So if you're a pregnant mother, you come into the office, a doctor's office, GI's office, and then the doctor flips a coin. 50% of the time, the mother will start smoking during pregnancy, and the other 50% of the time, they'll not smoke during pregnancy. Okay. Well, clearly, this is not acceptable in most moral, actually almost every moral standard of mankind. And so they had to come up with a kind of a way to answer some aspect of this question without randomizing smoking. And one clever way they did was as follows. They, instead of randomizing whether the mother would smoke or not during pregnancy, they actually randomized an encouragement to promote the mother to not smoke during pregnancy. So the key idea in their paper is essentially they will randomize an encouragement to not smoke during pregnancy. Okay. More specifically, they had two arms. Actually, they technically had three arms, but we're going to simplify to two just for the sake of demonstration. This arm consists of mothers who were encouraged to not smoke. And then this consists of mothers who got standard care, so to speak. Okay. So what does an encouragement look like in this particular instance? The doctor will give pamphlets, longer sessions during the office on please don't smoke during pregnancy, it's bad for your child. And then the standard care is equals to 1. The doctor really just did what the standard procedure at the end of the day. So it kind of bypassed the morality question here, randomizing smoking, to essentially randomizing the encouragement to not smoke at the end of the day. Now, based on this encouragement, then the mothers could choose to do one of the two aspects. They could continue to smoke. So this will be the mothers stop smoking, or actually not stop, did not smoke. And then here we can define as mothers who smoked. So, in an immoral world, we would randomize this guy, the actual smoking status. But what Sexton and Hubel did is to randomize the encouragement to not smoke at the end of the day. So, after randomly encouraging or not encouraging mothers to smoke, then the mothers could just decide at some point whether they smoked or not smoked at the end of the day. Now, if you read this paper carefully, they have a procedure on defining this more carefully. What does it mean to smoke during pregnancy? How many times do you smoke during pregnancy? But for the simplicity of just illustrating the principles, we're going to assume that there's a binary. You smoked or you did not smoke at the end of the day. Okay.
Can you say part 1 is exposure and part 2 is outcome?
Part 1 is exposure, part 1. You could think of this as an outcome, right? So you could think of the effect of encouragement on whether actually mothers stop smoking. And that is one effect that people study in IV. That's an important thing that they study. But we're going to go a little further because the original scientific question is the birth weight of the child. So this is the outcome of interest at the end of the day. Any questions?
In between, this is between outcome and exposure.
Between outcome, so this birth weight outcome and then this guy here. Yeah. Yes, so we're going to study that question. That's the other question that we'll study. Okay. By the way, this is also my first example of IB in second year PhD, and it's kind of lingered since then, and this is how I teach it. It's a nice example, definitely a bit idealized, but it kind of gets the concepts through by using a study design as the bedrock of how to define an IB. There's another way to define IB, which we'll talk about in the second part, which is an additive interaction, but that one, you essentially have to assume certain aspects of the effect doesn't exist, and it's kind of hard, or at least I would think it's kind of hard to imagine that scenario, but some may disagree. But in both cases, it's very interesting to study how the effect of unmeasured confounding works. Anyway, so in that particular instance, I just wanted to go through two things before I define counterfactual outcomes. Now, if, as one of the participants mentioned, if the encouragement is 100% successful, so by encouraging mothers to not smoke, every single mother decided not to smoke, and by not encouraging mothers to, smoke, then mothers did smoke. This is known as 100% compliance. And this would effectively mean that Z equals to A. So if the encouragement was 100% successful in inducing the A behavior, then essentially you can kind of go back to what we talked about as strong ignorability and then just do the, you can essentially, because now A is random. If Z equals to A, then A becomes random, and you can estimate it at the end of the day. Obviously, the correspondence between this and this is not going to be equal to each other, right? Sometimes, they might be encouraged, but they might still smoke anyway, or they might get the standard care, and then, a more careful mother might actually just decide not to smoke during pregnancy. Okay. So to kind of formalize that design, you need to, the modern literature defines two counterfactual types of quantities. So these two. This is the counterfactual outcome or counterfactual treatment status. And then this is the counterfactual outcome. And A and Z pair. Yes?
How to define counterfactual?
So you mean philosophically or like mathematically? There's a
Example.
Oh yeah, so I'll go through it. Yeah, I'll walk you through the actual word-by-word meaning of this. So, for example, this thing represents the counterfactual smoking status if every mother was encouraged to not smoke at the end of the day. Okay. So, if every mother was not encouraged to smoke, and if this was equal to 1, that means that every mother did not actually smoke during pregnancy. Okay. If, for example, this value is 0 for some mothers, that means that even though they were encouraged to smoke, ultimately they decided to smoke at the end of it.
Both extreme, maximum possible.
Yes. So this is this is idealized. The Sexton and Hebel paper actually kind of had a particular definition of what it means to smoke during pregnancy. But again, just for the sake of an introduction IV, we're going to binarize everything. In fact, really the more difficult part in non-binary case is really this guy. If this becomes non-binary, then identification, estimation, and everything kind of gets more complicated. But I'm happy to talk about that offline. Yes?
It's not a modeling question, but would this still pass the moral standards question today?
Excellent question. Third Anchor and I were debating this last semester. I don't think so, personally. But back in 1980, I wasn't born in 1980, so I have no idea. But presumably this passed some moral standard. I think this was published in JAMA. Yeah, but yeah, I think the society somewhat evolved since 1980. That's my feeling. But yes.
Quick question is, I said that the year is 1984, so it's prior to direct effect, a kind of proposal by Robbins and also by Pearl later. But could this be seen as kind of interested in the mediator's effect in a situation where the actual exposure has no natural direct effect or pure direct effect, right? Because basically, could you actually consider this problem as a mediation problem without direct effect?
Yeah, so it's an excellent question. So there's been works that kind of try to connect mediation of IV, and actually very recently by Eric and some of his former postdocs and students, they really try to leverage these connections between mediation and IV to really construct interesting efficient estimators. The assumptions are different. The target estimand is a little different. Mediation, they care about indirect and direct effects, whereas here they mainly care about the effect of A on Y at the end of the day. So it's a part of the mediation pathway. So because of this, the identifying assumption is a little different, but the also estimation strategy is a little different. Having said that, there's some overlap, and certain things, actually I have a paper that connects some of the work by Eric to Eric's estimator to make the IV estimator more efficient or more cost.
Is there any way you can check like Z affects Y only through A, not other way?
Is there a way, I didn't hear the first part.
Is there any way you can check that G affects Y only through A?
Yes and no. There's a way to falsify that exclusion. There's a way to falsify this thing. In general, that third assumption, this Z only affects Y through the outcome A, there's no direct way to check it. But my paper goes through a way to falsify it at the end of the day, using malaria as an example. Malaria Z is, and A is something else here. And there's also bounds approaches to do this as well to kind of falsify. In general, it's very difficult to have power to falsify this. If you think about it from a testing perspective, power to falsify this is quite low, unless you have a very far departure from exclusion restriction. Yes?
Just to be clear, so far we're not identifying.
We're not identifying. Yeah, we need to get to monotonicity and no additive interaction. But
could report back.
yeah. So actually, great question. So I actually did write. So all this lecture focuses on point identification of the treatment effect A on Y. If you're interested on just bounds of the treatment effect on Y, there are many interesting. Also, I wrote this here because I didn't do this. I don't know if you can see, but there's a paper by Swanson et al., Sonia Swanson in JASA in 2018. This is by far the most fantastic review paper on this literature. And there's also papers by Richardson and Robbins, Thomas here. I think, correct me if I'm wrong, Thomas, but I think it's 2014 in StatSci. And then if you want a textbook introduction, sorry, there's a book by Flores and Chen in Springer in 2018, if you're interested in the textbook version of this as well. So there are 3 ways to learn that material. Yes, Limbo.
There's also a very recent paper by Thomas and students.
Yes, there's a recent paper by Thomas and students on arXiv and on this, but just for the sake of an introductory lecture, we'll stick with point identification. But there are, so Sonia and I have written now 2 papers on this, 1 paper on this. There's a lot of various subtleties here that's really nice to actually explore, and this really really puts together all the subtle assumptions of a marginal independence and joint independence that Ilya mentioned briefly, and how that affects bounds at the end of the day. So if you're interested in partial identification, or the goal is to get a plausible range of the treatment effect, these are the 3 things at the end of the day. The high-level punchline, at least from my perspective, is that essentially you try to bound the counterfactual outcome based on the observable data, and almost in all instances it becomes a linear program, solution to a linear program at the end of it. Any questions or comments? Okay, so let's proceed with point identification. So there are a couple of things that you could be interested based on defining these search counterfactual quantities. One, it's known as the encouragement effect. Or it's the compliance rate, sometimes it's called, which is simply defined as the this guy. So this is the effect of encouraging mothers to smoke and whether they actually stop smoking. Okay. This is not the effect of encouraging mothers to smoke on the eventual birth weight or the actual usage of smoking status on birth weight. But with these new counterfactual quantities defined, you could define this little cute guy. This cute guy also has a lot of interesting statistical properties that I think is ignored in most of the literature in IB, but in the semi-parametric literature in IB, but this is one quantity that's estimated. The other quantity that's more popular and that's almost always reported in clinical trials, especially in the back of some supplement, is the intent to treat effect. This is known as the ITT. And then the intent to treat effect is roughly defined as the following. Let me be careful here. Quantity. Okay. So let me walk you through what this notation means. essentially, you can kind of imagine setting the value of A, treatment received, to be the value that what's known as a natural value of the counterfactual outcome, counterfactual treatment received for Z. If that's the case, you can define this particular quantity, which is the effect of encouragement on the outcome had the patient taken their natural value, their treatment receipt, minus the outcome, the outcome, counterfactual outcome under the no encouragement, and the mother or the patient took the natural value under the A0. Yes?
Clarify why A is lowercase and Z is uppercase and then Y.
They are all lowercase. I'm trying to write big, and so this looks like a big, but this is all tiny little lowercase. To be really precise, I should be saying Z equals to little z, but you know, imagine all this is just lowercase. Yeah, but thank you. Okay, so for this guy, you can actually estimate this and identify this using what's already known, what's already been in the design, which is that this design, this encouragement design, already satisfies 3 assumptions. And I'll go through these assumptions. So this is the first IV assumption. Based on that design, this thing satisfies essentially a version of Sutva . What does this mean in words? It means that the observed treatment receipt observes mother smoking status. The observed birth weight of the child is one instance of the 2 counterfactual outcomes for the A here, and one instance of the counterfactual outcomes here. One day checking on the natural value. Okay. And this is satisfied just based on the fact that the Z, the encouragement, was completely randomized. And hopefully, you know, there's no interference and other things. The second assumption that the randomized encouragement design satisfies is ignorability in the instrument Z. So again, this is joint for the sake of syntactical. So the second one says that the instrument, in this case, the encouragement, was randomized. Okay? And this, because it's randomized across all the counterfactuals, and this will be how it's represented. Okay? And the third one that the encouragement design satisfies by design is overlap. Okay? That there were some mothers who had a positive probability of treated, getting encouraged, and then there are some mothers who had a positive probability not getting encouraged. So just this little clever design already satisfies this, and this is important because once you have this, you can identify at least these 2 quantities, the encouragement effect and then the intended treat effect. So the encouragement effect can be identified really as just a difference in means. Okay. And this should come as not a shocker. Essentially, because the instrument was randomized, this encouragement was randomized, and we're only looking at like one outcome post-treatment. If you just pretend for a moment that this represents the outcome Y in the review slide, this should be fairly obvious that, you know, the encouragement effect should be just a difference in means between how many people are smoking among those who are encouraged versus how many people are smoking among those who are not encouraged. The second result, based on just these 3, is that this guy, we're going to just make this as the ITT effect. can also be identified by simply looking at the difference in the outcome and on the encouraged versus unencouraged. Okay. This one may take a little bit of moment, especially if you're not familiar with this type of notation, but if you kind of look at this a little bit, this is essentially just a function of z here. Okay? So as long as z is randomized, I can identify some mean of this quantity at the end of the day. And that essentially means that I can identify this intent to treat effect by just taking the difference in the observed outcome among those who are encouraged minus the mean of the outcome among those who are not encouraged. Any questions? So in the lecture notes, I also go through a missing data analogy. If this was not clear, I have an entire sub-lecture notes on how all this is connected to missing data in the context of IB. If you're interested, feel free to browse through that entirely, and then I'm happy to answer. Yes?
Is it intentional that you haven't drawn?
Not intentional. I like DAX, just FYI, but it's just, I want it to be, yeah, actually, I think it's partly because, you know, you can kind of convince these ideas without a DAG. You know, I'm happy to talk more. Hito has some conversations about DAGs in the particular context of this, but when I teach this material to undergrads, I actually teach it without a DAG. And that's not because I don't like DAGs, but I thought, at least my personal view is that everything can be motivated by the design, study design. And then if you kind of motivate everything by study design, you don't really necessarily need a DAG to explain. Because right now, I'm not even assuming that an unmeasured confounder exists. Like this entire thing piping through, I haven't assumed a U existed, actually. So there's some benefits of kind of thinking from a design. But again, there's some cons. If you're not familiar with the math here, the DAG is more communicative versus this kind of a more technical math approach of doing this. But yeah, there's pros and cons. Any other questions? Great. So, so now we're actually at the point where we discuss monotonicity. So these two are great in that we can identify the encouragement effect and the intent to treat effect, but these two are not really getting at the effect of the A on the outcome. For example, this only got at the effect of Z on A, this only got at the effect of Z on Y, but what I really want is the effect of A on Y at the end. Okay? And so to do that, you need to make some assumptions, and these are the assumptions that kind of make IB controversial, and some people move away from IB because of these assumptions. So let me go through that assumption. Okay, so to identify some causal effect of A on Y, we need these controversial assumptions. The first one is instrument relevance, which is roughly stated as this guy. So what does this mean? It just means that the encouragement effect is not zero. Okay? That means that the encouragement to not smoke during pregnancy had some effect on, like, not actually encouraging mothers to not smoke at the end of the day. This can be checked from data based on the exercise you went through by literally computing this number and seeing whether this number is far from zero. Yeah. Okay. So this is checkable. The next one, IV5, which is the exclusion restriction, is this guy. So let me walk you through what this means. Yes?
You wrote that it shouldn't be zero, but you said almost as if that it should be positive.
I'm going to get to why it's positive. Yes, I haven't gotten. But so with IV6, this needs to be positive.
Okay.
Yes, yes. So I haven't gotten there yet, but you're absolutely correct. Yeah. I'm actually glad that there's some of the audience actually knows this material and are asking me interesting questions. The other are seeing this for the first time in some sense at the end of the day.
Also wondering, you said, oh, we can actually just measure it, but that does assume that mothers would honestly report whether or not they smoke, which I could imagine might be tricky because you would maybe don't want to admit that you're doing something which is unhealthy for your unborn child.
Absolutely correct. So in the case, it's really difficult to measure this guy, and most likely there's measurement error here. In fact, it's an interesting case of binary measurement error. Usually measurement errors are studied under continuous cases, but this is binary. And the paper has a way of dealing with this qualitatively. What's interesting here is that in further IV theory, even if this is measured with some kind of error, this still goes through actually, and you can still identify the causal effect. I say some because if this is continuous, it's very obvious, but right now it's binary. If this is binary, even if this is measured with some version of measurement error, this will still go through. Yes?
Say a word about what Y of A could be in that context.
Y of A and that. Yeah, I mean, fantastic question. So in that particular context, you would actually define like an A star variable, which is the true latent smoking status, and it's usually binary if you stick with binary. If this is continuous, then this A star will be a latent kind of true smoking behavior, let's say number of packs of cigarettes, something like that. But again, this doesn't truly answer your further question, which is people might just not report, and this could downward bias your reported A at the end of the day, and I believe all the measurement models that I know for binary A does not account for that particular. So it's an open-ended area. But if you assume what's known as symmetric error, measurement error, this actually still goes through. That's a very advanced IV topic, but it is in an econometric split, if you're curious. Yes?
So IV4, if you have the average facts 0, but you have individual average facts that still violate.
All we need, at least for IV4, I'll get to IV6 where you need the individual effects, but the IV4 only requires the averages are not 0. But I'll just state this now, because everyone is itching to get to this, which is the, essentially you need a version of this guy. Okay. And so this is at the individual level. So the pair individual effect of A1 minus A0 has to always be non-negative for everyone in the population. And this is known as monotonicity. Okay. So these are the three assumptions. Now, a little pause. This is all stated in terms of superpopulation. I'm assuming there's some superpopulation entity that we sample from. This could all be rephrased under design-based. And the two papers that I cite at the very top of this, as well as my entire PhD thesis, at least two chapters of my thesis, is on a design-based version of all these assumptions, where you don't necessarily assume that this is even random. The only thing you assume is it's random. And you can reframe every assumption based on design-based as well. That's one thing. The second thing is, except for IV5, IV4 and IV6 could either be checked directly through data or be enforced by the study design. That is, you can there is a study design known as one-sided encouragement where you can actually enforce this always holds for every person. This you can check from that assumption there. Really the most problematic assumption is this guy. That conditional on the treatment receipt A, the value of the instrument has no longer play a role in the counterpart shock. Okay. Third comment. This could be stated entirely differently. Right now I'm assuming almost sure equality across this. You could state this in terms of expectations. You could state this in terms of probabilities. There's many versions of this. Personally, there's very limited practical differences. There's interesting theoretical differences, but there's limited practical differences between different ways of saying this guy at the end of the day. Yes?
I'm confused when you say the 6 we could enforce it, because that's actually the initial question I had with this setup, that you might imagine, not saying it's likely, but it's possible. Let's say you have a mom who actually is medically quite aware and she knows smoking is really bad and she loves to smoke. She realizes, well, I'm not going to smoke if I'm pregnant. That would just be plainly immoral. And surely any doctor would implicitly assume that that's not going to happen. By giving the encouragement, she infers from that, oh, maybe not as bad as I thought, because it's only saying maybe you shouldn't smoke. Therefore, she actually will smoke.
Yeah. No, in that particular design, in this particular case, there is going to be you cannot enforce this by design. In many development economic program evaluations, where imagine you replaced Z here with a new development economic program, and A here is whether the actual participant in the program used the program. If you don't have access to the new program, there's no way you can actually use it. In that case, this can be directly enforced. And I just want to briefly point that out. This is known as one-sided encouragement, which essentially happens a lot in development econ, and also many social policies where you can, by design, enforce this condition. So which simply says that if this always holds. Okay? So if you're under this standard program, you can never access the true new program at the end of the day. Sorry, let me get to limbo and then yes.
So you just made a comment that you can rewrite exclusion using introduction. Just curious how you do this without
Introducing what?
maybe.
So, excellent point. So to do it in the monotonicity-based approach, and I'll get to this in the next part, you can replace, in the no additive interaction part, you can replace this with an expectation. In the monotonicity-based approach, my understanding is that I don't know of a way to replace this. Maybe I should clarify my comment I will use the same assumption going through the no additive interaction effect. In the no additive interaction effect, you can actually replace this with an expectation. You cannot replace it here. You're right. Thank you for correcting that. Yeah, I was skipping myself. Thank you for the correction. Yeah.
Just want to make sure, like in the talk, the third assumption and IV5 are similar.
IV5 and what are similar? Yes, these two are similar. Yes, yes. Yeah, exactly. I apologize for not lining these things at the end, but yeah, exactly. Any other questions? Okay, so with these 6, we can actually arrive at our first. Actually, before I do that, I need to discuss probably the Nobel Prize winning idea. So it's important to break this down a little bit by partitioning the population into 4 types of people. Now, just to provide some history, this assumption, or a slight variation of this assumption, was stated in the Imbens and Angrist in the Econometrica paper, if I remember correctly, in early 1990s. This conceptualization of that assumption is in the Angrist, Imbens, and Rubens, the AIR paper in 1996 JASA, and really clarified what's happening here when you make this assumption to point identify. So you can kind of break the entire population by kind of looking at all possible ways that this A0 and A1 could realize. A0 and A1 could both be 1. That means that regardless of encouragement status, mothers will never smoke at the end of the day. This is the status where if the mother was not encouraged to smoke, then the mother would be smoking, and if the mother was not encouraged to smoke, encouraged to, so no encouragement, then the mother will be smoking. If the mother was encouraged not to smoke, then the mother will be not smoking. Yeah. This will be the opposite case where a mother was never encouraged to not smoke, but yet they ended up not smoking anyway. But when they were encouraged to not smoke, they started smoking. Okay. This is known as defiers. And then the final group of people is regardless of encouragement status, these mothers always smoke at the end of the day. So you can partition the population into 4, and this is an exclusive, mutual and exclusive population partition. And what the assumption essentially says is that you don't have this group, okay? Because that violates that last assumption at the end of the day, okay? And more high-level wise, what this is doing is essentially removing heterogeneity in the unmeasured confounding space, because this is essentially, in some sense, deriving the unmeasured confounding heterogeneity at the end by removing one of these effects. So that's what this does, A5. Now, with that reinterpretation, we can get to our final punchline result that ends today's first part of talk, which is we can identify what's known as the local average treatment effect, or complier average treatment effect. So consider this thing called a late, which by definition is the y1 minus y0 given a1 equals to 1 and a0 equals to 0. So this is the complier group. And a couple of things here that I didn't recognize when I was a PhD student, but now doing this so many years, I kind of see it as this estimand is only well defined if exclusion restriction holds, actually. So I don't, sometimes, you know, people try to define an estimate even before identifying assumptions. Surprisingly, for the late in 1996, this estimate only made sense after you defined that quantity at the end of the day. So that's some subtle point that I didn't realize when I read the first paper, but over the years looking at this, I realized this estimate is special compared to ATs or IATTs, is that the ATT or ATE is not dependent on how you define the assumptions, identify assumptions, but this one does. Yes?
Sorry, I'm confused about well-definedness. Is it, you mean it's not well-defined or it's not an effect?
Ooh, that's a good question. I think it's not a proper effect in the Frankakis and Rubin sense.
Okay, yeah, but if I ignore all that, if I like crack open the causality book about something, but define the function actually.
Yes. You could, yes, yeah.
I could define it, but it's not defined.
Well, yes, so I guess there are two ways I should be more precise, and thank you for giving me that. So you can define this without exclusion restriction. You can define a functional of the counterfactual outcomes that does not rely on IV5. There's an argument, though, as whether certain functionals make sense or not. And then I think the Frankakis and Rubin paper, which then precedes the IV paper, says that without this guy, like this doesn't really make scientific sense. Let's put it that way. Yeah. Well, because again, this is echoing Frankakis and Rubin. They wanted an estimate that's essentially restricted to a particular well-defined subgroup population, whether it be latent or non-latent, actually. If you have exclusion restriction violated, essentially you can't narrow it down to just a complier group. That's their argument.
Why is it? Because even if I don't have exclusion, I still have this subgroup.
Yeah, you can still have the subgroup, but then this quantity then expands into like a mixture of defiers, mixture of compliers, never takers, and always takers that have different effects and different pathways going through, right? I'm happy to talk it offline. Whether I believe this philosophy or not is a different question, but you know, this is a subtle point that I only realized recently. Yes?
Rana inventory when it showed to have a stochastic vector.
Yes, there is a stochastic. Yeah, so there is a stochastic version. Oh, yes, there is a stochastic version of this. I think it's on a probability scale, if I remember correctly, on this. It's not on the expectation scale, because there is a subtle thing about variance. Subtle thing about. Yeah, I'll get to the no additive interaction part. Yeah, but yeah, there is a probability version of this. All right, I'm running out of time. Let me say. So, if you're interested in the effect, and there's a long discussion whether you're interested in this effect, you can identify this effect using IV1 through IV6 by this guy. Okay. In effect, it's the ratios of that encouragement effect and the intent to treat effect. Okay? If you take the ratio of the intent to treat effect to the encouragement effect, you can identify this causal parameter, which is the effect of smoking, actual smoking, on the birth weight of the child among mothers who comply with the encouragement. I was going to go through a proof of this. I already ran out of time, so I'll stop here. Happy to take questions during break, and then I'll start the next part with the no-additive interaction.